Hello, good morning, Assalamu alaikum, namaskar, Saraswati here, and Ramadan Kareem. I'm very pleased to give you this lecture on in situ combustion. And the first thing I'll always like to point out is the oil prices, as you can see, is going up. So is the gas price, which is good news. So we will talk about in situ combustion, which is one of the enhanced oil recovery methods. And I have worked on many in situ combustion projects. In fact, I have designed 13 in situ combustion projects. I'll tell you a little bit about them in a few minutes. So we'll talk, I don't want to read all this, but in general, we'll talk about the in situ combustion mechanism, the different types of combustion, forward, reverse, combustion parameters. This is a big subject and we'll only touch upon it. Then in situ combustion problems, what are the actual problems in the reservoir as well in the operation? We'll say a few words about wet combustion and then field experience. And we'll say one or two words about combustion and steam injection comparison. And finally, the operational problems. And the last item is high pressure air injection, which is you could call it a variation of in situ combustion, but it's a different kind of process. Now, our target in all thermal recovery processes is really heavy oil and tar sands. You see here, heavy oil and tar sands. In the world, there are 5 to 8 trillion. Okay, this is billions of barrels. So 5,000 to 8,000 billion, 5 to 8 trillion with 12 zeros. USA has about 53. Canada and Venezuela have the largest. And there is still a lot more in Saudi Arabia, other countries. Now we have light oil too, and some of the light oil is also recoverable by thermal methods, such as steam injection and in situ combustion. So light oil is also a good target, provided the amount of oil in the reservoir is enough to justify. That is the key factor. So you'll see in the future that we'll have more applications of light oils. So if you look at the right side here, the target is huge, gigantic. The world consumes 34 billion barrels in 1 year. And you can see that we have 5 to 8 trillion barrels in the world. Now, a couple of quick words about the recovery factors. Recovery factor is a very important number for petroleum engineers. It means the fraction or the percentage of the oil which is in the reservoir that you can produce to the surface under the current technology and also under the current economic conditions. Well, given that solution gas drive primary recovery, take the primary recovery, then we'll talk about water flooding, which is secondary recovery. So for primary recovery, solution gas drive will give you 10 to 15% of the oil, light oil, but only 3 to 5% of heavy oil. So I'm showing you this number really to emphasize the heavy oil. Water drive, if you have water drive, then you can get 25 to 50% of the oil, but only 5 to 10% in heavy oil. Now, I have a lot of experience with water drive heavy oil reservoirs, and they are very difficult to exploit. Okay, after that, when we come to water flooding, we can recover 10 to 30% of a light oil, but very little, 5% or less of a heavy oil. Now, these numbers vary, of course, depending on the reservoir conditions and depending on the type of oil. Steam flooding. Now, here we are talking about heavy oil. It can recover 50 to 60% of a typical heavy oil, and also it can recover light oil if you have the right conditions. Cyclic steaming is only really applicable to heavy oils. Typically, you'll have 10%, but in some cases we've achieved 40%, 30% in Alberta. And then we have SAG-D, special variation of steam flooding. which has achieved 50% recovery. And finally, in situ combustion, which is the topic of today's talk. In situ combustion, although it has not been an economic success in most cases, it can recover quite a bit of the oil, actually 25 to 50%. So we'll talk more now about the last topic. Here are the different thermal recovery methods, and I have circled out the in situ combustion based processes. So this is in situ combustion. This is steam. This is hot water, really, which is a variation of steam. We discussed all that last time. And we have also electrical heating, which is, I've worked on several electrical heating projects, and I consider it to be mostly an experimental kind of thing, although we have done maybe a dozen projects in the field. So getting back to in situ combustion, there are three variations: forward combustion, reverse combustion, and high pressure air injection, which is really a cross between combustion, a thermal recovery, and a gas drive. Forward combustion can be dry or wet. Sometimes they use additives, and then THAI, toe to heel air injection, is a special variation of in situ combustion, and Capri is still another variation of in situ combustion. Let me put it this way, right up front, reverse combustion in general doesn't work. Additives don't work. Thai and Capri, don't touch them unless you want to do research. So I'm telling you, this is the state of the art. Things will change, and if I have time, I'll tell you the limitations of these. Okay, basic concepts of in situ combustion. Here is the most important one by far, which is the big selling point, that a portion of the reservoir oil, less than 10%, which we call fuel, sometimes they call it coke, this is what is actually consumed to generate heat in the reservoir. So we are burning, or you could say oxidizing, that's the proper word, a very small fraction of the oil in the reservoir to generate heat, which makes it very attractive to people, as you know. That's why people keep doing it. Now, if you want to oxidize something in any place in the reservoir, you have to inject oxygen, or in other words, maybe air. Well, we have injected air, we have injected oxygen, we have injected other gases, mixtures of oxygen and air, we've done all kinds of different things. Sometimes we call it enriched air, where we've added additional oxygen. So that is the most important part, that in situ combustion utilizes a portion, actually the most undesirable portion of the oil to generate heat, unlike, say, steam, where you have to generate steam at the surface. Now, fuel, again, I'll be using this term. This is the heaviest fraction of the oil, which is generated automatically in the reservoir to produce heat. Too much of this is good. Too much is, take it back. Too much is no good. Too little is no good. Too much means that you have to inject a lot of air. Too little means you don't have enough fuel to generate enough heat to heat the reservoir. Now, the last item is the most important one with combustion, that severe mechanical problems detract from the favorable features of combustion. So to give you a state of the art, right now there are how many in situ combustion projects in the world? 100? Exactly 2. There are maybe a couple of small ones, but the major projects, one is in Romania, Suplacu de Bacău, and one in India. I'm from India, and I worked actually in the early stages of that project in 1991-92. These 2 projects have been going on for many, many years. They are primarily government supported, and they produce perhaps 10, 12,000 barrels each, not very much. So there are 2 major in situ combustion projects. How many steam projects? Several hundred. I lost count. And the reason is very simple. The last item, that there are severe mechanical problems, and also another type of problem with the control of the front. Now, this is a diagram of in situ combustion. I'll show you a couple others too. There have been more than 200 field projects, actually 250. It's rarely economic. Several of them have been economic, barely economic. It's a very complex process, very difficult to control, and is dominated by gas flow, many mechanical problems. But they have a special place. That's the main thing to remember. There may be places where in situ combustion is the only choice, and then you have to be very careful how you design it. As I said, I've designed more than 13 actual projects which were actually implemented in the field. I could talk about them for hours if you want. But in situ combustion does have a place. I have spent a gigantic amount of time on in situ combustion. Still, I'm working on a project at this right at this point. So this diagram shows you how the fluids look. If you take a cross section of the field, we have flow. We are injecting air, and at this end we are producing gas, water, and oil, all three. Okay, the diagram is not to scale. Right in front of the air, in fact, in this part, we have hard sand. We have burned or displaced everything in the sand. It's clean, hard sand. And then we have a combustion zone, which is maybe 1 to 2 meters, 3, 4, 5 feet wide, very, very narrow. And then after that, there is a steam zone. The steam is formed from the water which was in the formation. So this steam goes and condenses here and forms a steam zone. And really, this steam zone is what displaces the oil, much like the steam processes in the last lecture. The steam zone will cause the formation of an oil bank, as you see in the picture. Now, as I say that this diagram is not to scale, the steam zone will be quite wide, maybe 20, 30, 40 feet, depending on the spacing of the wells, and the oil bank will have a similar size. Here are a couple of other diagrams of the same thing, taken from different sources. This is from the Department of Energy, which you see, probably you've seen it before. And this one thing which you see here is very, very, very realistic, is that you notice here, this is the formation thickness here. And this is the steam chamber. All steam chamber here, this blue, and this is the combustion. You can hardly see the combustion front. But what I'm trying to show you here is that everything is going up. Because you're dealing with a very large amount of air and gas, there is severe gravity segregation. All the fluids are going to the top. So the vertical sweep is very poor, and this gas will break through into the well very early, and then you have high temperature in the well bore and all that. There's no simple way to correct it. We have several ideas, but they really haven't worked. Now, one of the oldest paper on in situ combustion, which is still very useful, 1961, is by Nelson and McNeil. They were with Mobil Oil. Actually, I used to know them. And this diagram is from their paper. And here you see they don't show gravity segregation. They are showing essentially a relatively uniform advance of the fluids and the gas. What are the mechanisms? In situ combustion is a very complex process. First of all, the combustion zone acts, this is the important thing to remember, the combustion zone acts like a piston. It must either burn or consume or burn or displace everything ahead before it will advance. So you see that has a huge implication. If there is a lot of fuel, then that combustion zone must burn it. You must supply enough air or oxygen so that it burns it. If there is water, then it must displace it. So this is an important aspect of the mechanism. Thermal cracking occurs because the temperatures here are 700 degrees Fahrenheit or 450 degrees C, very high temperatures, which causes cracking of the oil, which causes the deposition of the heavy fractions. The heavy fractions is really like a very viscous liquid. It's not a solid. Gases vaporize the light oils and water. This is another important part of the mechanism. And then severe gravity segregation. The fluids go up to the top of the reservoir. The process is highly rate sensitive. The steam is also rate sensitive. And there's such a thing as a minimum flux. You have to have a certain minimum air injection rate, otherwise the front will go out. I'll show you that. And also sometimes air or oxygen will go ahead of the front, channeling in other words. It will cause low temperature oxidation, which is nothing but trouble. So it's a very complex process. Favorable features, in a couple of words only, a portion of the heavy oil or the heaviest sands are burned. And also we can inject water with air, which will limit the combustion. We can control combustion to some extent. But the most important thing is that we can use very large valley spacings. So in in-situ combustion, if you have these wells here, this is a producer, and this is injection well. So I'm showing you a plan view. This is the plan, and this is a 5-spot pattern. And so if you're doing a steam injection, the pattern size, which is the area in the pattern, will be of the order of 5 acres, which is about 2 hectares. If, on the other hand, you're doing in-situ combustion, you can have 10 acres, you can have even 20 acres. That is one of the big attractive features of in-situ combustion. It has its problems too, but we'll go further. Some of the unfavorable features, the biggest one is very high gas oil ratios. So we are producing oil at a gas oil ratio of 4, 5, 10,000, 10, 20,000, 30,000. I've seen even 100,000 SCF per barrel. So 10,000 SCF barrel is 2,000 cubic feet per cubic meter per cubic meter. Gas will limit liquid flow. Gravity segregation is a problem. Most of the reservoir is cold. This is very important to remember, that we have very high temperatures at the combustion front, but most of the reservoir is still cold and nothing much is happening there. So well productivity must be high at the reservoir temperature. And as I said earlier, that both high and low fuel contents are bad, because in one case there's not enough heat, in the other case you have to inject huge amounts of air. Now in-situ combustion has many variations, many in fact. I'll only mention 2 or 3. Forward combustion is what I showed you in the diagram, and the temperatures are of the order of 1,000, 1,200 Fahrenheit, or maybe 700 to 900 degrees C. We can move, in most cases, not always, but we can improve the process by water injection. You have to be very careful with water injection because water will go down. So you have to be careful how much you inject and where you inject. And oil must be sufficiently mobile at original condition. Because what I should have pointed out to you in this picture here, I said the combustion zone temperature is very high, 700 degrees Fahrenheit. What is the temperature here? The original reservoir temperature. So the mobility of oil and water must be high enough to support the air injection rate. That's a very important important point about in situ combustion. That's why combustion is often more successful in relatively light oils. It can be heavy, but still mobile. Now, reverse combustion is a different kind of process. I'll show you that in a diagram. The temperatures are much, much higher. Maybe they're of the order of 1800 degree, 1200 degrees C, 1300 degrees C. And also we have slow oxidation. I'll show you that. Don't use it. It doesn't work. It has its uses in coal gasification, okay, but in general, we haven't had any success with reverse combustion. It looks really good in the lab, by the way. I have written a couple of papers saying in reverse combustion is a good process, and they were based upon lab data in the old days. Here's a difference, a comparison of forward and reverse combustion. Let's take two diagrams, identical diagrams. Air injection well, producing well. Air injection well, producing well. Okay, same. And this is the formation thickness. Okay, now what you do, in the first case, ignite the formation in the injection well. Ignition, we don't have time to discuss that. That's a important part of in situ combustion operation. Ignition. Usually we'll do it by just air injection, or in other words, spontaneous ignition. We may inject steam for a while and then inject air, or we may use even an electrical heater, or we may even use a gas burner, okay? But we try to do it as simply as possible. But let's get back to what I was saying. We ignite the injection well here and then continue air injection. In the reverse combustion, we are not igniting the injection well, we are igniting the production well. In both cases, we are injecting air this way. You can see this here. So now what happens is that the injected air will propagate this front like this, and it will displace the fluids. In the second case, what's happening is that the air is going through the entire reservoir and arriving at this ignition point and supplying it with oxygen, and then only the combustion front will move opposite to the airflow. So what will happen now is this. Number one, the air has to go through all this oil, which is here, before it reaches the combustion front, and most of the oxygen will be used up in slow oxidation. And by the time it reaches here, maybe there's not enough oxygen. And the other thing is this, that this combustion front is now going through a very hot zone, is moving through initial oil and water. So in general, is reverse combustion. Dr. Dietz, he was the head of research in Shell in Rijswijk, Netherlands. He and I were very good friends. He once wrote to me and said that reverse combustion is seldom feasible. He said it will be feasible only under Arctic conditions. Now, combustion has many parameters: fuel content, air requirement, air-oil ratio, air injection rate, how much oil you're displacing from the unburned sand by indirect heating, water-air ratio, air, not water, oil, water-air ratio, extinction radius, how far the combustion will go before it will just become extinct, goes out, vertical sweep, aerial sweep. We'll talk about only a couple of these. First of all, before you do any in situ combustion test, you have to do a fire tube test. Fire tube test is just a lab test where we have a very complex tube here. It's shown just like a rectangle, but actually there are heaters outside like this, and there's a inside, there's a tube and a moving thermocouple, or sometimes we have other heaters inside. So it's very complex. So combustion tube test essentially means that you take the oil and the sand and the water in the right proportion, fill the tube, then ignite the tube on the top. and then inject air on the top, and the combustion zone will move. And as it moves, collect all the gases, liquids, everything. So this is all the equipment to do that, and analyze the gas for oxygen, CO2, CO, nitrogen, any hydrocarbons, any sulfur dioxide, any H2S, and then derive the parameters. So it's a very complex experiment, and a typical experiment, just one experiment will cost you about $150,000. And very few labs can do it. The University of Calgary has one of the most oldest and the biggest labs for doing this experiment. Also, the IRS in India, Institute of Reservoir Studies, it's not IRS in US, Institute of Reservoir Studies in Ahmedabad also has a tube. And Skoltech, do you know Skoltech is a beautiful new university in Moscow. I've been there a couple of times. And they too have a really good, really reliable, good tube to do these kind of tests. So a typical test will take almost 15 days work. That's why it costs so much. Typically, you must do about 6 tests on your oil before you'll have, let's say, enough data to have reliability. Now, fuel content, how much of the oil is burned or deposited is the most important single parameter. And it depends on just about everything. It depends on the quality of the oil. You look at all these different variables, oil properties, viscosity, composition, and also the rock properties, also the air injection rate, also the water saturation, and finally the temperature. So it's a very complex quantity. There are correlations which are no good, don't use them. The only reliable way to get a good fuel content is to do a fire tube test. Well, it's expensive, but you have to do it. So fuel content, typically it will be of the order of 1 to 3 pounds of fuel per cubic foot of rock. Okay. So in terms of SI units, it will be approximately it will be approximately 30 times that number. Okay. The next number, which is very important, before I go to that, the fuel deposition is by this reaction equation. Now, in a typical combustion process, there are 13 or 14 or 15 reactions, important reactions. Sometimes people narrow them down to 4, and that's why the simulations are not very reliable, and same goes for the lab tests. The lab tests are good for parameters, some parameters, but they won't give you a good number for oil recovery. Do not rely on the oil recovery numbers from either the lab test or from a numerical simulation. But lab tests are good for parameters. Some of the other lab tests, which I'm not discussing, will give you these constants, E and A, in the Arrhenius equation for different reactions. Okay, so you need to do a lot of reaction tests to get enough data for to determine the parameters. Okay, the other very important number is air requirement. How much air you need to have to burn through 1 cubic foot of rock? And it will be typically 200 to 300 SCF per cubic foot bulk volume of rock, or same number in standard cubic meter per cubic meter of the rock bulk. That's a very important number, and you can actually calculate it from the parameters. Now, we don't have time for the parameters. We need maybe 2 lectures to discuss the parameters. They are very useful, not difficult to calculate, and they all come from the fire tube test. So what does it say? It says that if you want to burn through 1 cubic foot of the rock, 1 cubic foot is only about this much, you need to inject 300 SCF of air. That's a huge amount of air. And how do you inject it? Well, it has to be compressed first of all, and you need compressors. Compressors are very, very expensive pieces of machinery. A steam generator is a dumb piece of machinery. A big steam generator, typical California, 50 million BTUs per hour will cost you maybe $1.5 million. A compressor, let's say 2 million SCF per day capacity, will cost you perhaps $10 million. And that's a low capacity, in fact. So air requirement is a very important number, and it will tell you also how much air you need to inject to burn through 1 cubic meter of rock or 1 cubic foot of rock. And given that number, you can actually calculate recovery. I can show you all that, but we don't have enough time. Air injection rate is another very important number. How fast can you inject air? This is the problem with the light oil reservoirs. In many light oil reservoirs, the permeability is low. The light oil occurs in sandstone carbonates, in Middle East, many carbonates. So the permeability K is low, maybe 20, 30, 40 millidarcies. In the case of most of the heavy, not always, but in most of the heavy oils, the permeability is high. K is high. And here you're talking about darcies. The permeability is of the order of darcies. 2 darcies, 3 darcies, typically in California, 3 darcies. So air injection rate is high. And air injection rate is crucial in situ combustion, because if the rate is too low, the fire will go out, extinction will occur. And then also if it is too high, then too we have a problem, we'll have channeling of air. So you have to be very careful with the air injection rate. The air can go, if this is a reservoir, all the air can go to the top and break through in the producing well. This is an injection well, this is a producing well, and the air can come right to well and leave all this oil behind. I've seen this so many times. So you can say combustion is a complex process, but we have learned an awful lot, so we can manage it. How much oil is displaced? Well, oil displaced is the oil which is in the formation minus the oil which is burned or consumed. It's a very simple calculation actually. If you have porosity, if you give me the air requirement, if you give me the time, I can give you the oil recovery. It's a simple calculation, maybe takes 10 minutes. But it's, the big problem is you have this, again, the gravity override of the air. And the question is, how much air is actually going through the oil? And that takes a lot of work and calculations. So that's why I wrote vertical sweep, which depends on the geology. Also the horizontal sweep, also what kind of a pattern you have and what kind of well completion you have. So in situ combustion depends on calculations, of course, but it also depends on an awful lot of experience. If you show me a reservoir, I'll tell you right away whether that's a good candidate for combustion, because I've seen many failures. Failures, you see, nobody writes papers on failures, okay? If you have a project, steam or combustion or any other EOR project, and it's a failure, maybe economic failure, maybe technical failure, whatever, you're not going to write a paper on it unless somebody forces you to do that. So you have to learn this from experience. Now, vertical sweep is a big subject, but let me just say this, that you have very strong override, because air density, what is the density of air? About 0.05 pounds per cubic foot at standard conditions. Oil is more like 60, 50, 60 pounds per cubic foot. So there's severe air segregation, gas segregation. And also, sometimes what we see is even worse, that you may have a fast-moving combustion front in the upper part of the sand and a slower front in the lower part of the sand. Very complex solution, very complex situation, and really we cannot do a whole lot about it. Now, we also have such a thing as wet combustion. Wet combustion is an invention of actually Shell Oil Company. Amoco, which doesn't exist anymore. Amoco also took credit for it. So did Exxon. Actually, the first paper on wet combustion came from about the same time, but I believe it's Shell's original idea. So the idea is this, that you may be able to inject certain amount of water with the air. How much water? Here are two limits. A typical one will be 300 barrels of water for 1 million cubic feet of air, or 1.7 kilogram of water per cubic meter of air. The other limit will be 1,200 barrels of water per million cubic feet of air, which will be about 6.7 kilograms per cubic meter. So what happens then? Well, in the normal wet combustion, which is about 300 barrels, we are hoping, or well, if there is no severe segregation, this is a reasonable number, that this amount of water will actually pick up the air, the heat in the air zone, which is hot zone with a lot of heat in it, and change into steam, and then push the oil further. In the second case, which is much more complex, I would say that you have to be very careful if you try it. We are actually injecting a very large amount of water, and we are actually quenching, putting out the fire. And then, because we have still air, the fire restarts further down, and it goes on like that. So you can imagine a combustion front which jumps from point to point. As I say, you have to be very careful. It's a very complex process. I already talked about that. Here's a picture. You can see it. It's a very idealized picture, you know. Dry combustion and wet combustion. Okay, compare the two. It's normal wet combustion. We have less than 2 kilograms of water per cubic meter of air. So imagine that you have this red hot zone, which is red, and you have a steam zone ahead of the red zone. So this is dry combustion. Now imagine that we are injecting some water. So what happens now that the water will pick up the heat from the hot sand, and it will create a steam zone further out here. So we are still leaving some hot sand. We are not completely cooling it down. Now the second diagram shows you the pressure. The pressure is very high here, then it goes down. And the third diagram shows the oil saturation. You can see that we have displaced oil to this distance for dry, but to a much greater distance in the wet combustion. So wet combustion looks really good on paper, but it's very difficult to successfully implement in the field. Now, if you look at the field experience within in situ combustion, we've done 250 projects. Maybe 10 of them have been economically successful, but the important thing is that they have all produced oil, anywhere from 10, 15% to 50%. Typically, the air oil ratio is 15,000. Now, you remember a steam oil ratio, how much steam you inject to produce 1 barrel of oil. Here we have how much air you need to inject to produce 1 barrel of oil. And a typical number will be 15,000, maybe if you're lucky, less, 10,000, maybe 5,000, initially at least. All of those are very high. Well, you know, if you look at the numbers, typically the total oil production worldwide by combustion is less than 50,000 barrels a day right now. Some experience in light oils. One of the earliest projects I did in my career was in Bradford, Pennsylvania, same field where we did also the steam project. Bradford is one of the oldest, or maybe the oldest reservoir in the world. I shouldn't say that really. In Pennsylvania, I used to live near there, and we tried to do in situ combustion in Bradford field 4 times. 4 times we tried that, and every time it was unsuccessful. And we didn't know much about it. I mean, I'm talking about 1954. That was before my time, to 61 period. So I saw really the last couple of projects, but I didn't see the earlier ones. It didn't work because the oil does not deposit enough fuel. So there's not enough heat. Okay, one of the successful projects on which I worked also is the fry test, marathons, fry test in Illinois. I helped to convert to water injection. And also we have all kinds of suggestions like oxygen enrichment to make up for low fuel. We did that too. Okay, with the steam, how does it compare with the steam? Well, number one, in a steam injection, the steam front advance requires that you must keep the entire area at the steam temperature. Okay. A steam injection involves essentially two-phase flow. Combustion, on the other hand, involves strongly three-phase flow. So what does it mean? Number one, it means that if you have a steam front, let's look from the top, this is the injection well, and this is all steam. All this zone should be at temperature of steam Ts. In the case of in situ combustion, we have a rim. The rim is where the temperatures are high, equal to Tc, the combustion temperature. But behind the front, this is the front I've drawn. Behind the front, doesn't matter what is the temperature. You can cool it down to 0 degrees C, this part. So that's a very important difference between the two. So the heat loss is much higher and the steam consumption is very high in steam injection. Now I'll go through some reservoir related issues very quickly because we don't have time. The biggest thing is that gas has much higher mobility than liquid. The vertical permeability is low, extinction occurs, low temperature oxidation occurs. The liquid mobility is low at the producers. And then we also, in carbonates, we have fracture burden. So these are, each of these topics merits a complete lecture. High gas mobility. Here is a diagram which shows you the relative mobility of gas to the total mobility of liquid. So what's the ratio? Well, the ratio is, as you can see, 0.1 here, and here it is 30. Only in this region, the mobility, the ratio of the two is of the order of 15 or higher. But all in this entire region of saturations, the gas has a far higher mobility than the liquid. So the ratio is very, very low. Low vertical sweep, I already discussed that. And this is the extinction. And this is a very, very interesting problem on which I did a lot of work over the years. Here's the air injection well. I'm showing you a plan view. And the combustion zone is advancing, advancing, advancing. And at some particular time t, it is where you see the shaded area here. So it has reached here, and it looks like this in the diagram above. So what's happening? You can see that if you're injecting air at a constant rate, the combustion zone will keep on slowing down. Slowing, until it is so slow that the heat loss takes up all the heat generated and extinction occurs. So if I take a cross-sectional view, so let's say we take a temperature along this cross-section, this one, then you see this. You have temperature on this scale and radial distance r on this scale. So at time t1, the temperature looks like this. Time t2, it looks like this. Time t3, it looks like this. And at time t4, the temperature looks like this. And this is the minimum combustion temperature. It says here, minimum combustion temperature. So the front temperature has now gone below the minimum combustion temperature. So at this radius, extinction has occurred. The fire has gone out. So that is one of the key factors you have to calculate to see how far the well should be. Low temperature oxidation is a huge subject. I can give you 5 lectures on that. Why does it occur? Where does it occur? But what does it do? It produces alcohols, alkalis, aldehydes, ketones, ethers, acids, you name it, and those are formed, they react with oil, and the formation gets plugged up by the products. One of the processes which has been suggested is toe to heel air injection, that you have a horizontal well as shown in the picture, and there is a series of vertical wells. Start the combustion zone here, and this supposedly advance as you see here in the picture, and it will go here like this and displace all the oil or bitumen. It doesn't work. Okay, two big expensive projects have been done, and the process is simply this: that the combustion zone goes very quickly to the horizontal well and burns it up. Don't do it. High pressure air injection is a different kind of process where we are injecting air at a high pressure in a light oil reservoir. So if it is successful, it could be workable in many kinds of reservoirs, and we can do it in very deep reservoirs, 10,000 feet, 3,000 meters. And it has been relatively successful. Right now, there is no project. Until recently, there were 7 projects run by Continental Resources in Wyoming. Now, none of them is operating because of various reasons. The problem with this process is that, first of all, the cost is high. Secondly, you have a very high air-oil ratio. Air injection rate has to be very high. But it's a process worth looking at. Advantages, here you can see all the advantages. The high, well, is good for deep reservoirs. Air is readily available. There's spontaneous ignition. And you're really generating flue gas. Flue gas is no good really, because it has mostly nitrogen, 85% nitrogen, which doesn't do any good. It has 15% CO2, which does reduce oil viscosity. However, it's a process which has been relatively successful. There are many problems with in situ combustion, especially the producing well problem. Well problems are what makes the combustion uneconomic. High gas rates, fines, and that high temperatures will literally melt your casing, tubing, everything, and all the other problems. And they lead to high bottom hole pressures, high downtime. I did a big survey one time for a company, and I found that on the basis of almost 100 combustion projects, 10% of the time was downtime. That's no good. Frequent well service and so forth. What we have learned is, number one, in situ combustion can be viable under certain conditions if you have very few heterogeneous. Heterogeneous reservoirs are no good for combustion. And if there's no bottom water and no gas cap and no clay, so you can see that you have to have very high quality reservoirs, and the oil should be mobile. And the oil must deposit enough fuel. And the oil saturation must be high. And if it is all true, then you say that why not use steam, which is much better, better proven. And you have to really weigh that very carefully. So these are the situations where combustion may be workable. If the formation is too thin, if it is too deep, if there's bottom water. Now, you can make a success of combustion sometimes, not always, if there is bottom water. The question is the bottom water active? And how much is there? Is this a whole ocean or is this only 10 feet? So there are places combustion may be workable, maybe desirable even. Numerical simulation of in-situ combustion, I've done an awful lot of work on that. I published the first paper on in-situ combustion simulation. My paper was the first paper, 1979 in SPE. But combustion simulation is a process, according to Dr. Dietz. He was the head of research in Netherlands, my close friend. He said, numerical simulation of in-situ combustion is beyond man and machine. Would you believe that? And he said that in 1975. And I assure you, it is still like that. And there are many reasons for that. I could talk hours about that. So here is the final slide. We have done more than 200 fire floods, and we have a good idea of the conditions where it may be successful. Okay. Sometimes combustion offers a solution where other processes are not applicable, but you have to be very careful that it is really applicable. High pressure air injection, which is a special variation of combustion, is a new version of combustion, which may have notable commercial success. We have some experience, with the 7 field projects. They are all published. Also, there is a chance of using, possibility of using horizontal vertical combinations. Also, you can use combustion after a steam flood. Now, you have to be very careful. Is there enough oil to justify it? Now, I didn't talk about the failures of combustion. There are many in-situ combustion projects have failed, and I could go into that too, depending on the situation. So that's the end of my lecture. And to conclude, I'll say in-situ combustion is a process which does have application, but you have to be very careful that you do a proper design. Thank you.